Hey everybody, this is Larry. This is me going over Q4 of the weekly contest 205. We moved max number of edges to keep graph fully traversable. So this one was, I think the hardest part about this one is proving greedy. So with minimum spanning tree, minimum spanning tree is a greedy algorithm, but in this case this is unweighted. So there's no weights on the graph. And this really tests your understanding of minimum spanning tree and spanning tree in general. So for me, I am able to figure it out because I had some inkling, and some of this is just experience. So if you don't get this immediately, or if you took you a long time, a lot of this is just knowledge and practice and having done similar problems before. I haven't done this problem before, or at least not in the last 10 years. But I still have some gut feeling that when I was doing the contest, I might not have the proof, but I just this thing. So basically the idea is that first you take all the type 3 edges, you create a spanning tree from, or as much as you can, you see which edges are needed, right? And this is the part where I wish I have drawings, but but it turns out that it doesn't really matter, because as long as you have greedy, because and let me bring up some paint things here real quick. But the idea is that why greedy works is because let's say you have a cycle that, let's say you have a cycle and you want to create a spanning tree out of this, or like a graph that has a cycle, right? And the way that you create a spanning tree is just that all of them are valid. It doesn't matter which one, or subset of those spanning trees will contain, will connect all the nodes of the cycle, and the number of edges will always be n-1. It doesn't even matter which one, right? So basically, from that, if this makes sense, let me find this thing. Yeah, so from that, let's say we have, where's my thingy? Let's say we have these nodes. Oh, geez, right? The thing to notice is that, why, there's something like weird about my thing, but sorry about that. Wanting some different, oh, there we go. Now I bring back toolbox. Okay, now I could draw a straight line. So, you have some, nodes that look like this, and now we only think about type 3 for a second. But the thing is that when you process all the type 3 nodes or type 3 edges, you're gonna basically have a subset of the nodes, right? So it could be, maybe, oh geez, let's say for sake of fun, the blue nodes are, oh man, that's what I get for not drawing good circles. Right, let's say we don't have, let's say all the blues are connected and all the reds are connected, right? From using all the edges of type 3. Well, it turns out that because of how the spanning tree, now you have a spanning forest that only consists of type 3 nodes, right? And to connect them, they're always going to use the same number of edges. And you could kind of prove this to yourself, but now let's look at one particular spanning tree. Let's say we look at these ones, and they're everything's connected, obviously, right? And the reason why, you have 1, 2, 3, 4, 5, 6, 7 nodes, right? So that means that no matter which 6 edges you take, there is a way to take 6 edges to connect all these nodes. Okay, so that's how I greedy with. Let me change back real quick. So that's how I use greedy on the type 3 edges, and then you can use the similar logic to add in the type 1 and the type 2 edges, one edge at a time, to complete getting the entire graph. Because then now you could do some math and you could draw it out to prove it to yourself that if the final graph is connected given a preset type 3 edges are already set and you have like these forests and you have to connect the forests? Well, the short answer is if there are m forests that are created by type 3 edges, then there's going to be at most m-1 edges that are kept by type 1, and also m-1 edges that are kept by type 2, right? So knowing all these things, you can just do it in a greedy way. And like I said, a lot of time I spent 8 minutes on this problem. A lot of it was trying to prove this in my head. And even though my proof during the contest wasn't as what I told you with respect to the drawing, but I think that's the foundation of how to get so that given a connected component, the spanning tree will always have n-1 edges, and that's kind of the definition to build on to get for this problem. So for me, for this one, I keep two union finds. So I use union find, and I always write these from scratch, but you could have just actually, you have a disjoint union disjoint set data structure. What is it called? Whatever, union find, right? Then basically I just have these things, and I take in the correct parent to kind of get the find. And then first, so even though this for loop is a little bit weird, but basically this is not a real edge sort. It's just maybe I should have handled this better. But during the contest, basically I just use this to sort so that it puts the 3 in the front is what this does. And now after that, we could go for one at a time. And basically, we want to use a type 3 edge if we want to use a type 3 edge if so in the beginning, I know that this looks a little bit weird, and now that I think about it, it is super weird. But at the time, I don't know, at the time, and during contests, I rather be more verbose and don't have to prove anything. But the short story is that because we sort these things by t is equal to 3, and that's the critical part, meaning we do the type 3 edges first. Parent A is always going to be equal to parent B the entire way. So this is actually extra for the U find part, but the union find you still need, right? And then after you process all the type 3 edges, now you have multiple spanning forests, and these things just counts whether the current edge that's coming in is an edge that connects two forests, right? So that's kind of the idea behind this problem. And at the very end, we just double check that the graph is connected, both for Alice and Bob. And if not, then you have to return -1. Otherwise, we return just the number of count that we get. So basically, so this so again, to recap, this constructs the minimum spanning forests, or it could be a tree at the end. And these will just look at the forests and then look at each edge to see if it connects two different forests in that Alice or Bob specific graph. So what is the complexity of this? So edges could be n. So edges is this number, right? It's 10 to the 5th. Technically, it could be n squared. N is equals the number of node, but because this is this is bounded by this, we'll just say y, right? So in theory, this is all of y. And because so let's say you didn't sort it. Let's just say you do a filter to do the 3 first, and then the 2 and the 1s you actually don't care in what order, so you could just separate them out. If you do it that way, then everything is dominated by the union. Each cell or each edge is dominated by the union cost, which is, let's just say, one or reverse argument function. I do path compression, but I don't do the by rank, so you could do your own analysis on that one. But roughly speaking, because you do O of 1-ish operation per edge, it's going to be O of y, where y is the number of edges. In terms of space, it's going to be O of v for the number of vertex, and yeah. So that's kind of the analysis for this problem. Let me know what you think. Hit the like button, hit the subscribe button, join me on Discord, and watch me solve it live during the contest next. This Bob, this and Bob. Maximum number of edges. What are these colors again? One, two. Well, okay. No, that doesn't make sense. No, there's no weight. Makes sense. Okay. I think this is okay. Would have gone that wrong actually. Oh, almost missed quick. Jeez. Maybe somebody anyway. Okay. Hey everybody. Yeah, thanks for watching this explanation of this video. Definitely give me feedback, ask questions, because the more questions you ask, more feedback you give me, then it lets me know what kind of answer to give you for next problems, right? And so I'm trying to learn from this. So yeah, hit the like button, hit the subscribe button, join me in Discord, and I will see y'all next contest. Bye bye.